and you
Yes,
can go
great.
on.
Thanks, Anna. Yeah, so it's really my pleasure to host Susanna, that I met already a couple of years. We coincide quite often. So Susanna holds a master's degree in biomedical engineering as well as a PhD in bioengineering and bioinformatics. So she's an expert in genomic data analysis and the development of bioinformatics tools. Currently, she is a co-founder and acts as a chief scientific officer at ENGENOME, where she leads innovative projects and the scientific progress of the company. Here, as I note, ENGENOME has become a lead software as a service, the so-called SaaS company offering the bioinformatics analysis of DNA data and, very importantly, the integration with phenotype. Susanna's current focus there is on harnessing generative AI technologies to enhance genomic data analysis. And I consider this talk extremely important to understand and participate in the rising role of AI in genetics. So with this, the floor is yours, Susanna. And as we say, we'll leave the questions to the end. Please raise your hand so that I'll see who is asking and I can give the room for them. Thanks. Looking forward, Susanna.
Thank you so much. Let me share my screen. Okay. Should be able to see my presentation.
Yes, perfect.
So first of all, thank you for this kind invitation and good afternoon, everyone. Today, together, we will explore how we can apply artificial intelligence to interpret genomic variants. And the goal is to present how the integration of AI in genomics can accelerate discoveries, but also enhance our understandings of genetics and of its implications. Just a quick introduction of myself and my company. I'm Chief Science Officer, and I'm one of the co-founders of ENGENOME. We are a bioinformatics company founded in 2016 with the mission to unleash the full potential of genomic medicine. And we specialize in developing bioinformatic products to analyze and interpret sequencing data, both for clinical and research applications. And the cornerstone of our approach is the integration of advanced AI algorithms to enhance our software solution. Our aim is to cooperate in solving the diagnostic challenge, since, as we all know well, today molecular diagnosis increasingly relies on sequencing tests to analyze a patient's genome with the aim of identifying causing variants, but a single patient has millions of genomic variants and clinicians struggle to find the causative one, if any. So what we do at ENGENOME is software development within the NGS, the next generation sequencing workflow, and we specialize in creating robust solutions for both secondary and tertiary data analysis. So our process starts with raw sequencing data and extends all the way to variant interpretation, ensuring that each step of the diagnostic pipeline is efficient and accurate. And a key distinguishing factor, as I mentioned, we have is the applications of AI modules to speed up and boost all the process. Since 2019, we have been commercializing our flagship product, that is EVI, a software as a service platform that automates the analysis and interpretation of genomic data. EVI is tailored for rare disease diagnosis. It's CE marked as in vitro medical device, and our company is certified for quality management, medical device compliant, and cybersecurity. So this highlights we are committed to safety and excellence. Now that I've briefly introduced myself and my company, we can focus on the aim of the presentation today, and we will try to outline how different methods and models from the field of artificial intelligence can be applied to facilitate the analysis of genetic data and more in detail to interpret genomic variants. To give a comprehensive view, we will start with a brief definition of AI, and we will try to follow its evolution from traditional rule-based expert system, that is the broader category we see here, through modern machine learning algorithms and up to the last advancements in generative AI that in the last 2 years have impacted our lives. And this will help us to understand how these diverse approaches can be applied to specific steps of data analysis in genetics based on the nature and the complexity of the problem they have to solve. So the broader definition we can give of artificial intelligence dates back to the 50s, and we can say that a machine is considered intelligent if it can pass the Turing test, that is a test that has been proposed by Alan Turing. And briefly, this test involves a human judge who interacts through a computer interface with both a machine and a human. And if the judge cannot distinguish the machine from the human, then the machine is said to have human-like intelligence. So under this definition, AI is an umbrella term for machines that want to mimic human behavior in terms of logic, perception, learning. So if we want to apply this broad definition of AI to genetics, we can include at least these three kind of algorithms and methods. We have natural language processing, NLP, that is the extraction of information from text, like finding HPO terms in a scientific text. Then we have knowledge representation, that is the organization of complex biological data into structured formats to facilitate analysis, like ontologies. And then we have automatic reasoning that enables the system to draw logical conclusions from input data, supporting decision-making in diagnosis, research, and so on. And an example of automated reasoning is the rule-based expert system. And for variant interpretation, we have a very good example of how we can apply it, because we have expert-approved guidelines like the ACMG criteria, and we can build an expert system that automatically apply these guidelines. Indeed, we can define if-then rules that serve as the foundation for the decision-making. We can build a knowledge base that is based on omic resources such as ClinVar, GNOMAD. And finally, we can implement the inference engine that is the core of the expert system. Basically, it applies the defined rules to the data, effectively thinking through the problem like a human expert. And this system weights the evidence from the sources and interprets the results, providing an indication of the variant's clinical relevance. In the slide, I reported an example of for benign variant classification with BA1 criteria that is quite popular among who does this work. And on the right, you can see the corresponding pseudocode block, so the implementation of this rule. And this is exactly the schema that is implemented at the core of the EVI platform. We have integrated a range of guidelines covering different variant types, including single nucleotide variants in DES, copy number, mitochondrial. We are actively working towards a deeper incorporation of clean gen specifications. And this rule set has been translated into code blocks. Omic data sources have been collected and preprocessed, and the rule engine can efficiently gather evidence and determine the final classification for each variant. This is the principle of functioning of our own variant interpretation system, but there are many variant interpretation softwares that more or less work according to this schema. Anyone with their own assumptions, like sometimes they can use proprietary data, but this is the flow that can be followed. So far, we have spoke about using rule-based expert system to analyze genetic variants. And in the methods I mentioned, there's no consideration for the data. There's no learning from data or using data to improve the behavior of the system. If we move down of one level from AI to machine learning, we find a subset of methods that learns directly from data. So it's effectively data-driven and not only uses this data to learn, but also to make decisions even when these models haven't been explicitly programmed for the task. When it comes to machine learning, we have to work primarily with two key approaches. On one hand, we have supervised learning, where we have labeled data, meaning that each input is paired with the correct output, and the system can learn from these examples to predict outcomes for new examples. So in essence, the model can learn from past example and use the relations he learned to analyze new data. On the other hand, on unsupervised learning, we work with unlabeled data. So there's no predefined correct output. And here the goal is to identify hidden patterns and structures in the data without any explicit guidance. As these algorithms processes the data, basically they naturally stratify data into clusters or groups, grouping together replicates that share similar characteristics. So they tend to spontaneously organize to identify insights about the data set. A very simple example of machine learning. As said, it all starts from data. So here we have a data set with shapes, and every shape has a label indicated, in this case, if it's a square or a triangle. And the challenge here is to describe this data with suitable features that are informative to discriminate triangles from square. If we do it properly, we will obtain a trained model able to correctly predict the label for new unseen examples, new unseen shapes, based on their similarities to the examples in the training set. So each example in our training set is called an instance and can be described by a set of features. For example, we can include the number of edges, the number of vertices, and these are relevant features to discriminate between squares and triangles. But we could also add other features like edge length or color that are not relevant, but it could also be confounding factors. Feature engineering, so the selection of the most informative feature, is one of the key and most delicate parts of machine learning. So this is a trivial example, but this point needs very high attention. Then we typically organize these features into a feature matrix, where each row represents an instance and each column the value of the features for that instance. And the last column here is the class. So it's the label that I want to predict for each example. The matrix is used to train the model. And that basically during the training, the algorithm learns the relationships between the feature values and the label. And there are many different machine learning models available, each tailored to fit specific data scenarios. So there's not one single model, but many different models to be selected according to the most relevant for the problem I want to solve. Once the model has been trained, we can use it to predict the label for new unseen examples. Here, we are showing a new example, and in this case, the model can predict it's a square, or in this case, a triangle, given only the value of the features. Typically, good models are able to predict the correct class in most cases, but real-world scenarios are often much more complex than this toy example. What can happen is that not all the possible scenarios have been represented in the training set, because maybe not just circles or triangles exist, but one day we will find to predict for a circle or a rectangle. And also confounding effects can happen, because in this example, by chance, all the squares were green, but I could also have a new example with a pink square, and it might be incorrectly predicted as a triangle if color has been changed, has been selected as feature. So it opens the point for some key consideration that have to be considered for designing machine learning model that basically can be summarized in feature engineering and training set selection. So the training set must be diverse and representative. Basically, it should capture all the variety of cases that the model is expected to encounter when predicting real-world data. The dataset should be balanced so that each class is equally represented, preventing bias towards a more frequent class. So I should avoid a training set of all squares and two triangles. The feature set should minimize irrelevant or misleading data. Features should be chosen carefully to be meaningful, relevant, and fully describing the phenomenon. And finally, the training set should be large enough to provide the model with a comprehensive view of the data. Variant interpretation can be approached as a machine learning problem. Each instance is a variant. We have to choose the right pool of features to allow our model to predict if the variant is pathogenic or benign, if it has an impact on the protein or not, and we have to train our model on a large enough training set of already classified variants. Here, an example of machine learning based in silico predictors from a review from 2022, where they have been categorized according to their nature. So we have in red analytical scores that are scores that are obtained by directly measuring or modeling specific properties of the variant without any data-driven learning. Then we have in blue the supervised machine learning scores. And here, like MoodPred, Polyfen, and Primate AI, they are built by training models on a set of data and on features that are computed for each variant. And then in purple, we have the ensemble machine learning scores. Basically, in this group, the machine learning models are built by combining the outputs of other existing methods. So the features of these models are the predictors generated by other tools. And then in black, we have enhanced ensemble methods where not only predictions from other models are used, but also new original features are integrated to further refine the predictions. And this categorization illustrates well how many ways machine learning can be employed to assess variant impact. But if we think about the problems I mentioned in the previous slide, we have to be aware that some of these issues may happen when dealing with genomic and variant data, because the training set must be diverse, but many genomic databases are biased towards certain population, like European population, or specific type of diseases. The training set should be balanced, but variant databases often contain far more benign variants than pathogenic ones, and basically variant interpretation is unbalanced by nature as a problem. The feature set should have the minimal possible noise, but genomic data often are noisy, inaccurate, with sequencing error, imprecise computational predictions. Features should be meaningful, relevant, and fully describing the observed phenomenon, but sometimes we do not have enough knowledge to design the features to be fully describing the observed phenomenon. And finally, the training set should have sufficient size, but the availability of labeled data for variant interpretation can be an impacting factor. Another aspect I would like to highlight is that in machine learning, the aim is to find a model that best separates between pathogenic and benign variants. Pathogenic are the red stars and benign variants are the green dots. If we use a model that is too simple to capture the underlying structure on data, we can incur in underfitting. So an underfit model performs poorly both on the training set and on new data because it fails to learn the essential patterns. Another risk is overfitting. It happens when we use a too complex model, and basically it starts to learn not only the underlying patterns, but also the noise that the training contains. And basically it just memorizes the example in the training set and is not able to apply this generalization on new data. So the sweet spot is optimal fitting. Basically, it happens when the model is just complex enough to capture the real patterns in the data without getting distracted by noise. So an optimally fitted model performs well on both the training data and the new unseen data, generalizing effectively to new examples. So far, we have seen machine learning-based scores to assess the impact of a variant, but we can use machine learning also for more complex tasks, like including clinical information of the patient in the variant interpretation process. Back in 2021, we were among the first groups to develop a machine learning model to prioritize variants, not only based on ACMG guidelines and in silico predictors, but also considering the patient's clinical context. And we developed this model called the suggested diagnosis to identify the candidate variants for the patient. Basically, we have built a machine learning model with different features that are the pathogenicity score, that basically is a score that represents how much the variant is pathogenic according to SMG classification. Then we have added a feature that represents the inheritance fit. Basically, it evaluates how well the transmission of the variant among family members aligns with the expected inheritance pattern of the disease. And finally, we use phenotypic fit. Basically, we measure how effectively the variant can explain the clinical phenotypes observed in the patient. By combining these three features, our models can prioritize variants based on their overall clinical significance, ensuring that those with the highest potential impact are reported in the short list of candidates and are reviewed first by experts. Back in 2021, this model was recognized as best performing genome interpretation method at the CAGI Challenge, that is an NIH-funded initiative. And since then, we have extensively updated and validated this model, ensuring it remains at the cutting edge of genomic interpretation, and some similar models have been developed. Another key point I wanted to touch today is that a key feature for machine learning model is transparency. And a model is transparent when we can clearly understand how it works, including the rationale behind the decision. And transparency is not only essential for refining and improving AI models, but it's also becoming a key requirement under emerging AI regulations. Black box models are characterized by internal decision-making process that is not transparent or easily interpretable by humans. So we can observe the inputs and the output, but the internal working is hidden, making it challenging to understand how the decisions or the predictions are made. On the other hand, transparent models are fully visible and with understandable internal working. So we can see input, output, but also how data is processed and how a given prediction is reached. But not all models are inherently transparent by design, and being transparent doesn't mean that the model performs well. So a field of AI has started to work to develop methods to make transparent also black box model. And one of these methods is explainable AI. We use and apply to our tools an explainable AI method that is called SHAP. It comes from game theory, and basically it tries to explain individuals' prediction made by a machine learning model by assigning a weight to each feature, quantifying its contribution to the final prediction. So in this schema, we have the three features, so pathogenicity, inheritance fit, and phenotypic similarity. And for each of them, we have a quantification that is represented by the arrows in red and in blue in the last plot that represent how much that specific feature has contributed to the single specific prediction. And the clinical score for each variant can be computed as the sum of these Shapley values. So in this example, we have that pathogenicity and phenotypic fit have a positive weight, while family inheritance doesn't. So maybe we are evaluating a variant that is highly pathogenic, explain the phenotypes of the patient, but the inheritance model doesn't match the one required for the associated conditions. Explainability can be applied to elucidate the decision-making process of the model and to give the users different information about the rationale of the classification, like in this, but also to extract other information, such as the a priori robustness of the description of the patient in terms of phenotypes, or the overlap of each single patient's phenotype with the candidate diagnosis. We can apply machine learning also to more complex scenarios, and digenic inheritance is one of these. We have developed a model to understand if two mutated genes together contribute to the diagnosis. To do this, we have designed ad hoc features that account for variant pathogenicity, but also gene-gene interaction and phenotypic overlap. And with this machine learning model, we can predict if a variant pair on two different genes is potentially pathogenic or not. We have mentioned supervised learning, but quick mention to unsupervised learning that I just introduced before. Here, the difference is that we do not have labeled training data. Okay, so we do not know if the shape I'm considering is a square or a triangle. And as before, we can design a feature matrix and use this to train the model. In this case, we do not have the output because we don't know it. But instead of learning to map inputs to output, here the point is uncover hidden patterns or structures within the data. For example, unsupervised methods can group similar instances into clusters. So when a new input is analyzed, the model doesn't classify it into a predefined category, but instead maps it near the instances with similar characteristics, showing which data points are most alike. So this approach is particularly useful in exploratory data analysis or scenarios where labeled data is scarce or unavailable. Now that we have understood what machine learning is and how important it is, we can move to the next level of artificial intelligence, that is deep learning. Deep learning is a subset of machine learning, and here we use artificial neural networks with many layers and this is why they are called deep architectures. And basically, they automatically learn representations and patterns from a huge amount of data. So if in traditional machine learning, we have to handcraft the features, in deep learning models, these features are automatically extracted at high level from raw data during the training procedure. And of course, it can be really useful in contexts like genetics, where large amount of data have been generated and where manual feature engineering is often impractical. Deep learning has its foundation in the 50s with the first artificial neuron designed by Rosenblatt. And basically, this is a very simple model. And this artificial neuron wants to mimic the behavior of a true human neuron, where the input we have a weighted sum of input, and if it's above a threshold, the neuron is active, otherwise it's inactive. Of course, this model that is called single layer perceptron is limited to learn only linearly separable patterns, but many artificial neurons can be combined together, and many layers of perceptrons can be compacted in the network, and this is why we call these architectures deep. It's referred to the number of hidden layers. And by adding and stacking these many hidden layers, we have developed what we use today as deep neural networks. The theoretical foundation for deep learning have been there for decades, but the adoption of deep neural networks took off in the last 10 years. And this is because times were mature both from the algorithmic and hardware point of view, because on one hand, we had the training algorithms like backpropagation that were developed, and on the other hand, we had advances in GPU technologies that dramatically increased computational speed and basically made it feasible to train these deep architectures like convolutional neural networks. The first examples of deep learning were linked to the vision and image recognition. This is one of the first examples, but they have evolved in these huge advancements we can see today also in our mobiles. But deep learning does not only work for image recognition, but it proved to be extremely useful also on the field of genomics. An open challenge in biology for years was how to resolve protein structure, and AlphaFold, developed by DeepMind, is a deep learning method that is excellent in this task. So basically, it's able to predict the structure of a protein based on the pseudo amino acid sequence. Indeed, it was awarded with the Nobel Prize for Chemistry in 2024. Another example, we have an algorithm that is called DeepC to identify pathogenic intergenic variants, and we use there is a variant coding algorithm that is deep variant, always developed by Google, that do not analyze alignment sequences as textual representation, but alignment images to find outliers and understand if there's a variant. This complexity comes with a cost. Indeed, the more complex a model is, the harder it is to interpret due to intricate internal processes. So a field of research that is very active is how to apply explainability and transparency approaches to understand how these models work. Okay, now our journey has come to the last step for now, at least, that is generative AI. And this is the kind of artificial intelligence that is able to generate new original content. If we think about generative AI, we think about ChatGPT. There's much more beyond that. Many models and new models come out every day. So it's a field where it's difficult to keep pace. Once again, it all started in Google in 2017 with a key paper that is called Attention is All You Need, where basically they explained the self-attention mechanism that is the core component of the transformer architecture used in natural language processing and many other AI tasks. And basically it allows the model to dynamically focus on different parts of the input. But let's better understand what a large language model is. We have different examples: ChatGPT, Llama, Bard, Claude, Perplexity, DeepSeek that has recently been proposed. Well, these models are large, meaning they have millions to billion parameters. And the training happened on the whole corpus of human knowledge and lasts for weeks on very important performance computing. And they are language models, so their focus is language. Can be simplified in predicting the next most likely word. They can manipulate text, summarize, generate content with the desired style, but they are not by nature domain expert. Just to give you a few numbers, the training of GPT-4 took around 5 to 6 months with 10,000 V100 GPUs that run for 150 days on full power with a huge amount of energy consumption. If we ask to these models what they think about a genetic variant, they give answers that in many cases are quite accurate. So they can interpret and give information about the gene, about the variant, interpret the nomenclature. We can then ask if we can have some references about the variant, but here some problems start to happen. Indeed, given its knowledge, its internal knowledge, basically the system suggests references that do not exist. They are likely, but if you look for these papers, they just do not exist. And this is because we have to be aware of what these models are meant for and what should be avoided. They are not domain-specific experts, so okay to summarize text, elaborate, adjust writing style, provide generic answers, suggest basic workflows, but they should not be used to retrieve highly specific factual data unless they are not equipped to do so, to perform complex mathematical calculations, even if on this field, many models are coming out that are exhibiting some mathematical capabilities. They cannot handle nomenclatures or ontologies, and they cannot generate or validate domain-specific information. And so they should not be used to interpret medical or clinical data. For this, if we want to apply generative AI to a field that is so delicate and unique like genomics, we should ensure the accuracy. We should be able to leverage all available data. We should avoid speculative or hallucinated responses and promote transparency. So we have different techniques that can be applied to give this capability to generative AI. Like we can supplement the information that these models need to define a summary or interpret a genomic variant through, as an example, retrieved augmented generation, by including knowledge from ontologies, by providing access to scientific papers or other sources of information, through named entity recognition that basically links sentences to concepts. So we have different weapons to equip these models for this task. And this is what we have tried to do with VarChat, that is the first generative AI genomic assistant. And basically, it is designed to search and condense the literature on human genetic variants in short and informative summaries. And this is how it works. You can input the variant, and the system scans the literature, finds the variant, and provides a summary with the references to the most relevant information, and allows the continuation of the conversation about that variant through dedicated questions. Okay, we have arrived at the end of this presentation. So as a take-home message, we can say that what's next, we still don't know, but there will be something next. We are in the AI boom era, so we expect that AI will play an increasingly critical role in everything, and also in analyzing genetic data, but validation remains crucial since AI is a tool and not a replacement. So human experts should remain always in full control of the decision-making process. And finally, a quote that I use to close this kind of talks, that is that AI won't replace humans, but humans with AI will replace human without AI. So thank you for the attention. And